Hey guys! In our previous lesson, we were introduced to the concept of work. Work is a concept that basically tells us how much of an effect a force has on an object. We also learned how to calculate work when the force and the displacement are in the same direction. In this lesson, we're going to learn how to calculate work when the force and displacement are in different directions. So let's get straight to it. Okay, before we do anything else, let's review the concept of work in physics. Suppose we place a book on a table. The book is subject to gravity, of course, but since it's not moving, we say that gravity is not performing any work on the book. But if we remove the table, the book drops to the floor. In this case, gravity has caused a displacement in the book. So we can say that gravity did perform some work on the book. We can see that in physics, work is a sort of measurement of how much a force actually affects an object. So that's the basic idea of what work is all about. Now, the full mathematical definition of work is beyond our level of knowledge, but we can consider special cases of the definition which apply only to certain situations. The simplest case is when the force is constant and the displacement is in the same direction as the force. In such a scenario, there's a very simple formula for the work. It says that work is equal to the magnitude of the force times the magnitude of the displacement. To make the equation less cluttered, we can simply rewrite it as W equals F multiplied by D. F without the arrow represents the magnitude of the force, and D is just the magnitude of the displacement, in other words, the distance. Now here's the thing about this formula though. We have to be very careful to check that the conditions actually hold before we use this formula. In many cases, that's not a problem. After all, lots of forces are constant, like gravity near the Earth's surface. And it's not hard to imagine that, much of the time, the displacement of an object is in the same direction as the force itself. So it seems like the conditions aren't particularly restrictive. But there are lots of simple situations where these conditions do not hold. For example, it's not hard to imagine a case where forces aren't constant. Let's say someone is pulling a big, heavy box. And while the box is moving, the person could begin to pull harder in the middle of the motion. Our formula doesn't apply to such cases since the force would not be constant. It would be nice if we could find one that did, but as it turns out, the case of a changing force actually introduces complications which would be too difficult to deal with at the moment. So let's continue to assume that the force is constant and look at the case where the force and the displacement point in different directions instead. Doesn't it seem a little bizarre to have a force pointing in one way and the displacement pointing in the other? After all, if an object is being pushed on by a force, shouldn't it be displaced in the same direction as the force? Actually, not always. Let's say we've got a cannon that shoots a cannonball. The displacement is horizontal, but what about the force? Well, once the cannonball is in the air, the only force that applies is gravity, which is vertical. So here's a situation where the force and the displacement are in different directions. What would the work be in a case like this? Well, think about it this way. How much did the force of gravity contribute to the horizontal motion of the cannonball? The answer is, it didn't contribute anything at all. It acted purely to pull the cannonball downward. It didn't help at all in pulling the cannonball to the right. So that suggests that the force of gravity did no work on the cannonball. It seems a little strange, but it's true. Since the force of gravity didn't contribute to the displacement, which was purely horizontal, the work it did is 0. But wait a minute. The cannonball did move vertically at some point, and gravity obviously contributed to the downward motion of the cannonball. So shouldn't we say that gravity did perform some work? Well, the thing is, we're only interested in the displacement of the cannonball. It doesn't matter that the cannonball went up and down. It only matters that the final position is directly to the right of the initial position, so the net effect of gravity is that it did absolutely nothing. Okay, so here's what we know so far. If the force and the displacement are in the same direction, then the work done is F times d. If the force and the displacement are at right angles to each other, then the work is 0. That's because the force doesn't contribute to the displacement of the object at all. But, what if the two vectors are at another angle, like this? What would the work be in this case? Well, to answer that question, let's impose a coordinate system on this diagram. We have one axis running in the same direction as the displacement, and another axis that's perpendicular to it. And hey, once we do this, we can break apart our force into components. One component of the force is parallel to the displacement, and the other component is perpendicular to it. Clearly, the parallel component is the only one that contributes to the displacement of the object. The perpendicular component contributes nothing. Okay, so let's throw out the perpendicular component of the force and keep only the parallel component. The parallel component obviously has the same direction as the displacement itself. And if we assume that the force is constant, the parallel component of the force must be constant too. So the parallel component of the force satisfies all the conditions for the equation. Work equals F times d. So we can write W equals F parallel times d. So the parallel component of the force satisfies all the conditions for the equation, work equals F times d. So we can write W equals F parallel times d. And this new equation holds even if the force and the displacement are in different directions. So now we've managed to remove a restriction on our definition of work. Instead of insisting that force and displacement are in the same direction, we can say that the work done by a constant force is equal to the magnitude of the component of the force that's parallel to the displacement times the magnitude of the displacement. But wait a minute. Shouldn't it be fairly easy to figure out the magnitude of the parallel component? That seems like something we've done before. And indeed, it's only a matter of simple trigonometry. If we focus on this triangle here, then this length represents the magnitude of the force itself, and this length represents the magnitude of the component that's parallel to the displacement. If we know the angle between these two lines, then we can use trigonometry to find the magnitude of the force. We won't go through all the details here, but it's not too difficult to calculate that the parallel component is equal to the magnitude of the force times the cosine of the angle. So going back to our formula, we can rewrite it as the magnitude of the force times the magnitude of the displacement times cosine theta, where theta is the angle between the displacement and the force. Finally, we've found the formula for the work done by a constant force. This equation is very important, so let's go through it one more time. When a constant force acts on an object, the work done by the force is equal to F times d cosine theta, where F is the magnitude of the force, d is the distance, and theta is the angle between the force and the displacement. Awesome! Now let's look at an example to see how we can apply this formula. Suppose we have a rope tied to a 100 kilogram box, and it's at a 45-degree angle to the ground. Someone pulls on the other end of the rope, with the result that the tension in the rope is a constant 200 newtons. The box moves 10 meters to the right. We want to calculate the work done by the rope on the box using the formula for work, W equals F d cosine theta. What would our answer be for the amount of work done in this example? Well, the answer is roughly 1,414.21 joules. We can get that by simply substituting the values into the formula for work, W equals Fd cosine theta. Remember, F is the magnitude of the force. We know the magnitude of the force applied by the rope, it's 200 newtons. As for d, that's the magnitude of the displacement. Well, the box moved 10 meters to the right, so d is 10 meters. As for theta, that's the angle between the displacement and the force. Well, the angle between the displacement and the force is 45 degrees. As for the weight in this example, it's actually irrelevant, so we don't even need to consider it at all. Great, and once we substitute all these numbers into the formula, we can use a calculator to find out that the rope does roughly 1,414.21 joules of work on the box. Awesome! Now let's look at one more example. Here's a 50-kilogram box attached to a rope. The rope passes over a pulley, someone pulls on the rope, and the box is raised by 1 meter. Clearly, gravity is acting on the box, so we want to calculate the work done by gravity on the box. Now, this example is a little trickier, but since the force of gravity is constant, we can use the formula W equals F times D cosine theta. So what would the work done by gravity on the box be in this example? Well, the answer is negative 490.5 joules. And how did we calculate that? First of all, we need to figure out the force of gravity on the box. To do that, we have to use Newton's second law. So let's pull that up. So here, we can actually substitute the mass and the gravitational acceleration into the formula to find that the force is 490.5 newtons downward. As for the displacement, we're given that it's 1 meter upward. And what about the angle between the displacement and the force of gravity? Since they point in opposite directions, it's 180 degrees. And once we substitute all this information into the equation and compute it, we get a result of negative 490.5 joules. But wait a minute, negative 490.5 joules? What on earth does that negative sign mean? Well, the interpretation is actually quite simple. Remember, the displacement of the box was upward, against the force of gravity. Gravity naturally pulls things downward. In other words, instead of contributing to the movement of the box, gravity actually hindered the motion. So that's what the negative sign means. It tells us that gravity actually acted against the movement of the box. By the way, remember the example of the cannonball? We said earlier that because the cannonball lands directly to the right of the cannon, the work done by gravity is 0. That's despite the fact that the cannonball actually does move vertically. We explained this earlier by saying that we're only interested in the displacement and not in the path taken by the cannonball. That's true, but now we can think about it in another way too. Notice how the cannonball moves upward in the first half of the trajectory and downward in the second half? In other words, the cannonball moves against gravity in the first half and together with gravity in the second. So the work done by gravity is negative at first, then positive afterward. And these values end up canceling out, so the net effect is that gravity doesn't do any work. Awesome! And that brings us to the end of this lesson on how to calculate work when the force and displacement are in different directions. So we hope you try out more examples to get the hang of this concept, and until next time, have a good one.